Hello, I'm Alexander Rose, the Executive Director here at Long Now. Today, I'm going to be joined by Sean Carroll from Caltech and Santa Fe Institute, who's a theoretical physicist who's been really studying the nature of time itself and the human experience of time and really how we fit in it. And here at Long Now, we've been doing talks that kind of relate to time in many ways, but this is the first time that we're doing it on time itself. I'm very excited to have Sean here. Welcome, Sean Carroll.
Thanks very much, Xander. It's a great pleasure to be talking about time, the nature of time, what it means for all of us at the Long Now Foundation. Obviously, folks at Long Now have been thinking very carefully about time, about the human aspects of time, about how to measure it, how to think about it. And that's my jam. That's what I'm very, very interested in doing. You know, time is just so important to who we are as human beings, right? We feel like time is passing around us or we're flowing through time. The metaphors, they go back and forth. I'm not sure whether we're moving through time or time is moving around us. But either way, time is just crucial to what it means to be a person. We plan for the future. We remember the past. Some of us are so fascinated by the nature of time that we become professional physicists and we learn about what time means from the physicist's point of view. And we learn a lot. Like, physicists understand a great deal about the nature of time. But there's something interesting, maybe a little scary, that happens when you learn about time from the perspective of physicists. You learn equations, they tell you how physical systems evolve, but this idea that time passes or that time flows or that somehow we move through time, that central, most obvious idea about time in our everyday lives, disappears. It's nowhere to be found in the fundamental laws of physics, but it's clearly there in our everyday lives. And we think that we're made of things that follow the fundamental laws of physics. So what is going on? That's what I want to talk about with you today, how to reconcile how physicists think about time with how we experience it in our everyday lives, and what that reconciliation teaches us for what time means and what it means to be a person. So let me start by explaining what I mean when I say that this passage of time notion disappears when you learn about time from the physicist's point of view. What does a physicist do? What's a typical physicist kind of problem to contemplate? Okay, well, think about the planets in the solar system moving around the sun. This is the kind of thing that physicists are really good at. Paradigmatic. Kepler, Galileo, Newton, those people. You're given the state of some physical system, by which in this case we mean the positions of all the planets, where they're located in space, and how they're moving, right? The velocity at just one moment of time. You don't need to be given the history of the planets. At one moment of time, you're given where they are and how they're moving right now. And then you have a recipe. You have the laws of physics. You have Newton's laws of motion and Newton's law of gravitation. And from those, you can predict the future. From the present state of the system, you can tell where it's going to be next. You can predict eclipses in the future. You can say where the planets are going to be. You can make an almanac, okay? But there's something extra that is very, very important. You can also predict the past, or retrodict if you prefer. Given the current state of the system, the laws of physics tell you exactly what was going on in the entire past history of the system. And real astronomers actually do this. They extrapolate the current state of the solar system millions or billions of years into the past and the future. So buried underneath that little discussion is an idea that we call conservation of information. All of the information you need about the system right now, its positions, its velocities, and so forth, suffices to predict the entire future and past of the system. If I told you exactly the state of the system 1,000,000 years ago, you could predict what it would be doing right now. This is the disappearance of this idea that time is flowing. Time, to a physicist, ever since Isaac Newton, it becomes kind of a label. There's this moment, there's the past moment, there's the future moment. There's nothing special about what we call now or the present moment. The laws of physics describe every moment of time as being on an equal footing, and the information contained in every moment of time persists into the past and the future. That's very different from what we're used to in our everyday lives. Just as one simple example, imagine you come across, there's a glass of water on the table. It's a slightly cool glass of water, okay? And you ask yourself, well, what was the state of that glass of water a few minutes ago? Maybe it was just a cool glass of water just sitting there, but maybe it was a glass of room temperature water with some ice cubes in it, and maybe those ice cubes melted and cooled off the water. The point is, just given the macroscopic observable information about the world, you can't say where it came from. Unlike the perfect information we have for the solar system in the real world, where we see the glass of water and we can see a little bit about it, right? Its temperature, whether there's ice in it or not, but we're not looking at every atom or molecule of water, then suddenly information is no longer conserved. There's information that used to be there in the system. Did it have an ice cube in it or not? And that's disappeared over time. We have an irreversible process. So what we're seeing in the macroscopic world is what scientists and philosophers call the arrow of time, the difference between the past and the future. In particular, the asymmetry that we have when we think about now versus the past versus the future. And that asymmetry, that arrow of time, is not there in the fundamental laws of physics. We have to dig in a little bit to understand where it comes from. So let me just explain how that asymmetry between past and future shows up in our everyday lives. One aspect is that there is an asymmetry of knowledge, okay? In a very real sense, you can predict the future, but you're never really sure what's going to happen, right? Sometimes our predictions come out wrong. Whereas when it comes to the past, we can have records, we can have memories. There are things that exist in the universe right now, which we're very, very confident tell us something specific about an event that happened in the past, whether it's a photograph or a book or a fossil, a bone underneath the earth. These are artifacts right now that represent something definite about the past. We don't have photographs or artifacts that tell us about the future in the same way. But there's another asymmetry, not just knowledge between past and future. There's an asymmetry of influence between the past and future. We have in our minds the idea that the past is settled, right? It happened. There's nothing you can do about it. Whereas toward the future, we can make choices. We can do things now that affect the future. If you lift your left hand versus lifting your right hand, that might have an impact on the future, but nobody thinks that by doing something right now, you can influence the past. Where did these asymmetries come from? Why is it that we can know more about the past, but we can influence the future in some way? Again, it's nowhere in Newton's laws of motion, okay? Nor in any update of Newton's laws of motion. General relativity, electromagnetism, Schrodinger's equation in quantum mechanics, all of these attempts at finding a fundamental laws of physics have the feature that they treat the past, present, and future equally. Now, I'm not going to hold you in suspense too much. I actually know the answer to this question. Why is the past, present, and future so different to us? The answer is something called entropy and the second law of thermodynamics. I'm sure you've heard about this before. Entropy is basically, roughly, not exactly, but close enough, the disorderliness of a system, the randomness, the disorganization. And there is a law of nature that is true in our macroscopic everyday world that says that entropy increases over time. So a typical example might be an egg. You can have an unbroken egg. It's easy enough to break the egg to scramble the egg. And in that process, from unbroken to broken to scrambled, the entropy of the egg increases. You're mixing things up. You're making them more random. And that would just happen very easily and naturally in the world. Whereas, if you saw a movie of scrambled eggs reforming into an unbroken egg, you would know right away someone was playing the movie backwards in time. There's a directionality to the evolution of these systems. So the first law of thermodynamics just says energy is constant. That's good. The second law says that entropy increases over time in a closed, isolated system or in the universe as a whole. You can clean up your room, don't get me wrong. You can lower the entropy in a localized system by influencing it from the outside world. But overall, in the universe as a whole, entropy increases over time. So unlike Newton's laws or other attempts at fundamental laws of physics, the second law of thermodynamics does tell the difference between the past, present, and future. It says that entropy will be higher in the future. It was lower in the past. Good, that's nice. That's an explanation of something, but we want to do better. Why is it the case? Why does entropy go up over time? So this was roughly speaking solved in the 1870s by Ludwig Boltzmann, an Austrian physicist, and some of his friends. What they did was they said entropy is not just a rough idea, it's a highly precise quantitative concept that we can attach equations to. That's what physicists like to do with their lives, attach equations to things you thought you understood. So entropy, in Boltzmann formulation, is just, look, when you look at a system, a macroscopic thing, a glass of water with an ice cube in it, or cream and coffee, or an egg, you don't see every little bit of that system. You don't see the molecules. You don't see the atoms of which it is made. So let's take cream and coffee as a classic example, okay? If the cream and coffee are separate from each other, there's a number of ways you could imagine changing the positions of the individual molecules in the cream or molecules in the coffee so that macroscopically you wouldn't be able to tell the difference. But if you started mixing them together, if you started taking the cream and mixing it into the coffee, you would be able to tell the difference. So there's a small number of rearrangements you could imagine. Whereas if it's all mixed up, right? If all the cream and all the coffee are mixed together, then there are a large number of ways you can rearrange the atoms and molecules to make it look exactly the same. So Boltzmann says that's what entropy is. Entropy is a way of counting how many ways there are to rearrange the fundamental constituents of a system so that it macroscopically looks the same to us. From that point of view, it's not at all surprising that entropy goes up as a function of time. It's simply because there are more ways to be high entropy than to be low entropy. If you have a medium entropy system and just let it go, let it do its thing, let it evolve into the universe, it will naturally increase in entropy since there are so many more configurations that look that way. That part is easy. The hard part is, if you have a medium entropy system, why was it lower entropy in the past? If it started lower entropy, you can explain why, but you seem to need a new principle to explain that. And indeed, that is exactly true. Think of the arrow of time this way. There's no arrow of space, right? If you were an astronaut floating out there in space, there'd be no difference between up, down, left, right, forward, backward. But you know if you're here on Earth, there's an arrow of space, you can tell the difference between up and down. Nobody thinks that arrow of space is deeply ingrained in the fundamental nature of reality. It's just because you're in the vicinity of an influential object, the Earth. The same story is true for the arrow of time. The arrow of time, according to modern physics, is not built into the fundamental nature of reality. We experience it because we live in the aftermath of an influential event, the Big Bang, 14 billion years ago. For reasons that cosmologists do not understand, the Big Bang was very low entropy. The early universe was very orderly compared to what it could have been. Now, why is that true? Good question. Very active research question at the frontiers of modern cosmology. But for our purposes today, we don't know why. But it's true. The Big Bang had a low entropy. And once you say that, it's clear that entropy is going to go up. It's been going up for the last 14 billion years. It's going to continue to go up billions and billions of years into the future. So good, we think we know what entropy is, the number of ways you can rearrange a system. We think it makes sense that entropy increases over time. What we're left to do is understand what this has to do with our experience of time in the everyday world. How does that help explain this asymmetry we have about the past versus the future? This feeling that we have that we're flowing through time. Well, let's just take one example. Here's my favorite example of an asymmetry. This is an asymmetry of prediction versus records. You're walking down the street, you look down the sidewalk, you see a broken egg. And we ask ourselves, because we're in a philosophical mood, what is the future of that egg likely to hold? You don't know, right? There's many different possible things that could happen to the egg. It could just sit there. It could be cleaned up by somebody. There could be a rainstorm washing it away. There's many possible futures open. But if you asked yourself, what does the past of that egg probably involve? With very high confidence, you will believe that there used to be an unbroken egg and it got dropped and it broke. So right away, just seeing this thing in the world right now, this artifact, broken egg on the sidewalk, you infer a difference between the past history of that egg and the future history of that egg. Why? Well, It's not because of the fundamental laws of physics. Given the configuration today, egg on the ground, messy, etc., there are many, many arrangements of the individual molecules that could account for that. And accordingly, there are many, many possible futures. As we said, many things could happen to the egg. If all you knew were the fundamental laws of physics, there is a precisely equal number of past things that the egg could have gone through. The conservation of information convinces us that the number of past possible histories of that egg is exactly equal to the number of future possible histories of that egg. But there is one big difference, that we know the universe started with the Big Bang. And that Big Bang had a very low entropy. This is what philosophers call the past hypothesis of low entropy in the universe. So we know two things. We know the current state of the egg, and we know the initial condition that we started with very low entropy. That's where the imbalance comes from. That's where we know a little bit something more about the past than about the future. And we can use that information to say, given the existence of a broken egg on the sidewalk today, and the existence of a very, very low entropy Big Bang, we can infer that there used to be an unbroken egg. As you go through your life, as you are remembering things and predicting things about the future, you are constantly relying on the fact that the entropy of the universe was very low near the Big Bang. You might not have known that you are relying on that fact, but it's crucially important to how we live our lives. That's the good news. We can say something about where this asymmetry comes from, this asymmetry of both knowledge and influence toward the past and the future. But it raises kind of another worry that we didn't have before, which is the following. If all that happens over the history of the universe is that disorder increases, how did I get here? I think of myself as relatively orderly, right? The organs of my body, the neurons in my brain, they're organized in kind of a precise way. How could you tell me that something as exquisitely organized as a living being just came to exist out of increasing entropy over time? And of course, because I'm asking you this question, that I know what the answer is to this. At least I know a little bit. This is another active research area. But let's go back to our favorite example of the cream mixing into coffee. It begins in a very low entropy state. The cream and the coffee mix together. It ends up in a high entropy state. But that early low entropy state is very simple, right? All the cream's on the top, all the coffee's on the bottom. That final high entropy state is also very simple. Everything's mixed together. It's in between. It's that intermediate state on the journey from low entropy to high entropy where things look complicated, where the cream and the coffee are mixing together in unpredictable ways, forming little swirls, little fractal patterns that would require a lot of information to specify. So that's the secret, and we have a lot to learn still to go about this, but basically, complexity naturally arises on the journey from low entropy to high entropy. This is we think, a fundamental feature of how the universe works. That there's something about the journey from a simple beginning with very, very low entropy to a simple ending with very, very high entropy that can give rise to complexity. So entropy just goes up, but complexity first goes up and then goes down. It's a temporary phenomenon, which might make you pleased to understand what's going on, maybe a little worried about the ephemeral nature of things like that in the universe. And indeed, this is not just a story about cream and coffee. This is a story we can tell about the universe as a whole. The Big Bang was about 14 billion years ago, and right after the Big Bang, the universe was very low entropy, also very simple. It was hot, dense, smooth, rapidly expanding. That's all you need to know. Over time, what happens is the universe expands and cools, and structures begin to form. Gravity pulls things together, and we can see this. We can take an image of the background radiation from the Big Bang from a few 100,000 years after the beginning. You can see the first faint traces of structures forming. Today, 14 billion years later, our universe is rich with structures. There are planets, stars, galaxies, people, clusters, voids. It's a very lumpy, interesting, exciting kind of universe. But that's temporary. It's not going to last forever. Stars use up their fuel. They burn out. They go dark. Stars fall into black holes. Even black holes don't last forever. In the 1970s, Stephen Hawking taught us black holes radiate out into the universe and eventually evaporate away completely. We think, roughly speaking, that 10 to the 100 years from now, which is a long time even by long now standards, all of the black holes in the universe will have evaporated away into almost nothing. We think that the universe is expanding and it's going to keep expanding forever. We don't know that for sure. Remember, predicting the future is hard, but that's the best current theory we have. So the very far future of the universe is very high entropy, but once again, very, very simple. We, for what it's worth, live in the exciting part of the history of the universe, and we are part of that excitement. And maybe this is a story you're willing to believe on general grounds, complexity comes and goes, etc. But the leap from there to the specific complexity of a living organism might be a little bit hard to swallow, right? In fact, you're taught sometimes, I wish you weren't, but it's true, you're taught that living organisms are somehow fighting against entropy. They're resisting entropy, right? I think the opposite of that is true. My friend Michael Russell, who's one of the world's leading researchers in the beginning of life, the origin of life here on Earth, once told me the purpose of life is to hydrogenate carbon dioxide. Now, that might not be the purpose of your life, but what he meant was, why did life start in the first place? In his theory, and no one agrees, okay? There's a very large number of different theories that are competing right now, but he has one of the interesting ones. Russell says there was an overabundance of carbon dioxide in the early Earth. And that was a low entropy way for those carbon atoms to be. It would be much higher entropy for those carbon atoms to get rid of their oxygen and take on hydrogen, convert into methane, okay? Hydrogenate the carbon dioxide. The problem was there's no simple way to get from there to here, from carbon dioxide to methane. No simple reaction makes that happen. What does make it happen is a complex network of reactions under exactly the right circumstances. So Russell used this idea to make a prediction that underneath the oceans, there should be warm hydrothermal vents of a very, very specific chemistry. And after he made that prediction, it was shown to be true. We found things like the Lost City Formation at the bottom of the Atlantic Ocean, a warm hydrothermal vent, which have exactly this complex chemical structure. And Russell's idea is that this network of chemical reactions can get caught up in a vessel, a cell membrane, break away and form a precursor to life here on Earth. Now again, we don't know. It's one theory. But the point I'm trying to make is the existence of life is not something that is a struggle against the growth of entropy. It is something that is made possible by the growth of entropy. And once you have that, once you have these little complex networks that are using up the entropy around them, they can last for a long time. And I want to emphasize this because this goes into not just the origin of life, but what you are doing right now, the nature of us as bodies and beings here in the world. Roughly speaking, you can think about things that persist, okay? Configurations of matter that last for a long time. There's two ways to be a persistent object here in the world. One way is to be made of individual pieces, individual atoms and molecules that are themselves more or less stationary. We might call this microstasis. The chair underneath you right now is made of a whole series of molecules that are held together in a rigid pattern. They're not doing anything. They're not going anywhere. There's a solidity to it which maintains over time. But there's another paradigm, which we might call homeostasis, where you have patterns that persist over time, even that the individual pieces that make up those patterns are moving. That sounds a lot more like life to me, right? It's not just life. Think about the great red spot on Jupiter. This is a storm, okay? This is a storm of swirling gases in the atmosphere of Jupiter that has persisted for hundreds of years. It's not that there's one lump there that is absolutely stationary. The pattern maintains over time. That's what you are. That's what I am. We are patterns that get maintained over time because there's a lot of activity beneath the surface. You can try your best to be completely stationary, right? You can still your breathing, lower your heart rate, enter a meditative state. But whether you notice it or not, at the cellular level, there's a lot of action going on. A lot of ATP molecules are being created and used. ATPs are little batteries that fuel your system. You can stay as still as you want, but if you plop your body out there in the desert, away from fuel, away from water and food and so forth, you will not last for very long. What we really do is we maintain the persistence of the patterns we call our body by taking in fuel from the outside and using that for maintenance, for homeostasis. Why is that possible? Because entropy is increasing. All of those processes that keep us maintained require an increase in entropy of the universe. Here on Earth, mostly that comes from the sun, right? We think to ourselves, what does the sun do for us in terms of life here on Earth? The sun gives us energy, you might be tempted to say, and that's true. But it's not the whole story. The Earth radiates into space just as much energy as it gets from the sun. The total amount of energy here on Earth is not really changing that much. The difference is, for every 1 photon of light we get from the sun, the Earth radiates 20 photons into outer space. We get visible light from the sun. We radiate infrared light out into space. So 20 photons of infrared with 1/20th of the energy each is what we do to the energy we get from the sun. So in other words, the sun gives us energy in a low entropy form, 1 photon. We increase its entropy. We do photosynthesis, we eat our food, we think, we listen to talks, we make great speeches, then we radiate out into the universe the same energy we got, but with a much higher entropy. That's what enables all of the marvelous activity that brings us to life here on Earth. And that process is, to come back to where we started, what explains the idea that we feel that time is passing around us. That imbalance between past, present, and future caused by the fact that entropy is increasing. So if you think about it, you think about yourself right now at the present moment. You are in some configuration, right? Your body is doing some particular thing. And a day ago or a second ago, it was also in some particular configuration. A second from now or a day from now, it will be in some particular configuration. But you don't know, right? You don't have exact knowledge. You have vague knowledge of what your body's doing right now. You don't even have perfect knowledge of that. You kind of have a memory of where it was, and you can predict where it will be. And let's think about that process, not at the scale of days or years, but of seconds or milliseconds, okay? The point is, we are constantly carrying with us in our minds an image of our body. And not just an image of our body right now. We have a pretty good idea of what our bodies are doing right now, even though it's imperfect, right? We don't have perfect knowledge of anything. We also carry around where our body was. We carry the memory of what we were doing just a tiny fraction of a second ago. And we project into the future. Our brains are constantly doing this. They're making predictions about where we will be, where our bodily configuration will be a fraction of the second in the future. And they're constantly comparing its prediction as we made it to what we're perceiving as where we are right now and to what we think we were doing in the past. It is that constant process of comparison, past, present, and future on millisecond timescales. That's what gives us the feeling that time is passing, the feeling that we are moving through time because there's an imbalance. We know a little bit more about the past. We make predictions about the future. We constantly take in more data, more information, and we update. And every single update gives us the impression that we are moving through time. That's not just us, of course. That's not just human beings. Every animal species does something like this. But we human beings do a little bit more than the average animal species. We think about the future in different ways, okay? Every animal species needs to react to its present circumstance. But you know that human beings can react to a lot more than a fraction of a second, right? We can think about the future. We can contemplate it. We can plan. We can imagine different possible futures. That is a very precious gift that took a long time for evolution to give us. Malcolm McIver, who is a neuroscientist at Northwestern University, has a theory about this. His theory is that it comes back down to the first fish that climbed onto land. Okay, you may have heard of the fossil Tiktaalik, which is probably one of the first fish that climbed onto land. And McIver's idea is that when you're a fish, you can't see that far in front of you. Even if you're in very clear water, the attenuation length of light in water is only a few meters. You see things in front of you, but not very far away. So all of the evolutionary pressure when you live in the water is to see something and react to it right away. Is it friend? Is it foe? Is it food? Whereas when you climb onto land, now you can see forever, roughly speaking, right? On a clear day, there's no obstacle to how far you can see. You can see things so far away, it will take you time to interact with them in some way. And therefore, a new possibility opens up for evolution to choose to develop in your brain, which is the possibility to see something and rather than just instantly react to it, think about the possible things you could do. Hypothesize different scenarios, imagine them. This idea is the birth of imagination. And in fact, you can see how evolution did this. Evolution uses things over and over again, and neuroscientists have shown that the part of your brain that lights up when you're imagining a scene in the future is the same part of your brain that lights up when you're remembering a scene from the past. It's this ability to imagine different future hypothetical scenarios that really has reached its apotheosis in human beings. We are better than this, at this, than any other species of animals. And this is what really makes us particularly human. You could talk about this in many different ways. Here's an example, La Sagrada Familia. This is a cathedral in Barcelona, and it was constructed back in 1883 under the guidance of Antoni Gaudi. He took over from other people who started it, but Gaudi designed what he thought the cathedral should look like. It's an absolute masterwork, very, very complicated, a million different moving parts and different kinds of styles and so forth. And Gaudi passed away in 1926. And the cathedral was nowhere near finished when he passed away, and he knew perfectly well that it would not be finished when he passed away. But he still wanted to do it, even though he knew it wouldn't be finished when he died. What is going on? What's going on is Gaudi could use his brain to imagine what it would be like in that future time when the cathedral was done, and it made him happy then. The point is not that Gaudi thought that he would be a ghostly persistence over time that would be looking down on the cathedral and admiring it. He gained pleasure right at that moment from the prospect of the future. And that's something that we humans have the ability to do. The conditions of ourselves right now depend out on our visions of the past and the future, as well as our conditions here in the present. So it all goes back to the cream mixing into the coffee, okay? Entropy increasing over time. That's the story of the passage of time in the universe. But it's that middle phase where the cream is mixing into the coffee, where those little swirls develop. Those swirls are us. That's what you and I are. We are temporary little bits of complex structure in the universe that are part of the overall increase of entropy over time. That means we are ephemeral. We're not going to last forever. That's the bad news, okay? We're not going to last for 10 to the 10 to the 10 years. We have a lifespan. We have an expiration date. But it also means we are interesting. We are the interesting part of the universe. Part of this complexity is our ability to think about and model ourselves and the rest of the universe, to do what psychologists call mental time travel, to imagine ourselves, not just in different places, but at different times. It's that ability, that imagination, that flow through time that makes us what we are as human beings.